Hi there and welcome to this PowerCrest video on Introduction to Power Systems Protection. Right, this is a basic introduction to the fundamental concepts of power system protection. So I hope that you'll find it a relaxed introduction to the art of protecting a power system and that you'll enjoy this video with me. Right, so let's get started. The topics I'll be covering are the need for a protection system. Why do we need protection systems? Right? What are the qualities of a protection system? The components of a protection system, and finally, the types of protection system out there. Right? In particular, I'll be looking at the protection tree. So the need for protection system. Well, protection systems are really the watchdogs of the power system. They continually monitor, right, what happens in the power system. And their function is to detect any abnormal condition and to initiate the corrective action required, right, should the abnormal condition arise. So they're the watchdogs that watch, they monitor continually, and should they detect anything out of the ordinary, then they'll initiate the corrective action. Why? Well, not in order of priority. We have that the protection system should ensure that there is continuity of supply, right? If there is a faulted item, a faulted section of the network, that should be removed as fast as possible, usually, so that supply can still be maintained to the rest of the network. Also, and this would be, I suppose, rather obvious, to minimize damage and repair costs, and also to minimize risk of danger to people and animals, right? Minimize any hazard to um, workers on the site, anybody that may come into contact with the power system in some way. We want to minimize the risk of danger to them. And really, a system without protection would eventually self-destruct. Well, what are the qualities of a protection system? Well, we note that to maintain continuity of supply, the protection system serves to preserve the rest of the system from the destructive effects due to a part of the system having faulted. Now, in order to do its job properly, a protection system is required to have certain qualities, what we call the 4 S's and an R. The first S is speed. Protection should be as fast as possible, limited only by grading and stability requirements. Right? We also could say grading is selectivity. Grading requirements, selectivity requirements. The second S stands for selectivity. Only the minimum number of protection devices closest to the fault need be operated to completely isolate the fault. And this sort of opposes speed. Right, we can see in this diagram over here, we have a fault on line 1. We only want breaker A and breaker B to operate. Why? They're the closest to the fault, and these are the minimum number of breakers required to operate to isolate the fault. Right. If there is only one source at A, we could even say that only A needs to operate, B not necessarily. If there's a fault on line 2 at F2, right, we would want D to operate and not A or B or C or E. Right. D is the closest, and so in order for selectivity to be maintained, only D needs to operate for the fault F2. But we can appreciate that in order to allow D to operate first, A would need to be time delayed, slowed down so that it can allow D to operate first, and in the event D fails, then A can operate in backup mode. But this means A is slowed down, so we see that selectivity over here opposes speed. The next S stands for stability. Protection must be stable for out-of-zone faults, must not operate when not called upon to do so, and strictly, stability only applies to unit systems. So let's look at our network again. A fault F on line L2, right, would really be a through fault for line L1, which means we want the protection at A and B to be stable for this through fault condition. It must not operate when not called upon to do so. The last S is sensitivity. The protection needs to be as sensitive as possible, yet it must be stable for through fault conditions. So we see sensitivity, stability, they tend to oppose each other as well. Now, sensitivity is defined as the level of fault current at which operation commences, right? And it's expressed either in primary amps or as a percentage of our current transformer ratio. And as I've just mentioned, it opposes stability. So let's look at our system again. We have a fault at point F over here at the end of line L2, right? We would like the breaker at A to detect that fault as well, so that in the event of D not operating, the circuit breaker at A can then isolate that fault. However, in order to do so, it needs to be able to detect the fault at F, right, under minimum fault conditions. In other words, for the minimum fault current, we need to have A still detecting it. So, to detect that fault under minimum conditions, we need to consider a couple of factors. One would be the impedance to the fault, right? So we need to look at the line impedance of line L1, the impedance of line L2. We need to consider a phase-to-phase fault at F, right? Phase-to-phase faults are less than three-phase faults and are typically about 86% of the three-phase fault value. That's if we don't have any rotating plant in the immediate vicinity. Rotating plant being motors or generators. So as a rule of thumb, we always have the phase-to-phase fault being around 86% of the three-phase fault at a given location in the power system. Fault resistance, right? If there's any fault resistance in F, then this needs to be factored into the setting at A. And of course the minimum system voltage. Typically this would be around 90% of nominal voltage. So we need to determine what the fault current would be when we have minimum system voltage, right? And of course, as we said, for a phase-to-phase fault, and allowing for some fault resistance as well. The R stands for reliability. Reliability could be subdivided into dependability. The protection must operate when called upon to do so, right? And to improve dependability, we have often on important strategic systems, we have dual main systems, or we have main and backup systems, which is intended to improve the dependability of the protection scheme. We also have security. The protection must not operate when not required to do so. So we see that reliability can be further subdivided into dependability and security. Note that reliability applies to the actual protection scheme as a whole, right? We're looking at the hardware, the software, and the instrument transformers, right? And of course the circuit breaker. All these are considered when considering the reliability of the protection scheme. Here we have a photo of a protection system which is really not reliable. This is a boson protection scheme where the actual wiring, right, had become undone from the actual lug. Probably a bit of crimping that wasn't done too good. So the wiring became loose, and this is the wiring on a CT circuit. And as you may be or may not be aware, open circuited CTs are not good news, right? So we have arcing having occurred over here, and we can see substantial damage to the actual wiring and to the terminals as well. So what happened was that the boson scheme operated quite a few times under load conditions because of what had happened here. And obviously the scheme was not reliable. Right here we can see the damage, the extensive damage that has occurred to the terminals. Okay, moving on. We can see we have speed, selectivity, stability, sensitivity, the 4 S's, and reliability. The question I'd like to ask is, which is the most important of them all? Which of these qualities would you think is the most important one? In my books, the winner is speed. Right? The protection system should be as fast as possible, limited only by grading and stability requirements. Right, the components of a protection system, right? Quick overview is we have circuit breakers, fuses, we have instrument transformers, we have battery systems, and we have protection relays. And I could probably add in communication systems as well, which is part of many protection systems out there as well. Arguably, one could say they're part of the protection scheme. Anyway, those are, in a nutshell, really the essential components of a protection system: breakers, fuses, instrument transformers, battery systems, and the protection relay. Now, the protection tree. This is really an overview of how protection systems could be classified. Right? This is not the only way, but this is one way in which I found to be pretty useful in classifying protection systems. Right, so we can have primary protection systems such as fuses, series strip coils. In other words, the protection devices are directly inserted into the primary system. But most commonly, the protection systems interface with the primary system by means of instrument transformers, our CTs and VTs, and these we call secondary protection systems. They may be further subdivided into unit and non-unit protection systems. Right? With unit protection systems, we are talking about protection systems where the actual the area of operation of the protection system is well defined. There's well-defined boundaries. Right? Normally the location of the current transformers. So any fault within the area bounded by the current transformers is where our unit protection should operate. That's our area of operation. Anything outside the unit protection should not operate. It should remain stable. So unit protection systems are also normally fast. Normally there's no time delay on the unit protection system, or with the unit protection system, sorry. So we can have differential protection, accelerated distance, overcurrent high set, and other. Right? Differential protection systems could be our voltage balance or current balance. Right? Current balance being the most common. We can have high impedance, such as restricted earth fault, high impedance boson generator differential, or we could have low impedance, right? Where we have bias differential, sol core, etc. Accelerated distance, we could have permissive overreach transfer tripping schemes, permissive unreach transfer tripping schemes, etc. And overcurrent high set. Now, the overcurrent element really by itself is not really a unit protection system, right? It would be classified really as non-unit. That's why we see the overcurrent sitting over here. But in certain instances, by virtue of its setting, the overcurrent HiSet is actually a unit protection system, as it um, will operate without any time delay for a fault in a given area of operation in that boundaries. The boundary being defined by the location of the CT to which the overcurrent HiSet relay is connected, and the reach, right, the overcurrent element reach, which would be well defined for a HiSet element. Then we, of course, we have some um, other unit protection systems, as I've indicated over here. On the non-unit side, we've got overcurrent, and we have step distance. So I hope you've enjoyed this PowerCrest presentation on power systems protection, the introduction to the fundamental concepts of power systems protection. And please do subscribe, share, like, comment. I would really appreciate it. And I would like to invite you to visit my website, www.powercrest.net. Thank you, and until next time.